far as the header is concerned, we will just go back to so we could just look at it from here. So, and it's pretty self-explanatory and everything as far as the ARP header, pretty much which type of hardware you're using. The majority of the time, this basically is going to be Ethernet, what protocol you're using. Of course, this ARP is going to be for telling you the hardware size, the protocol size, ARP code, what's the MAC address, IP address. So basically for this particular packet here, as far as when it came out, let you know that it's me that's the source, IP address, MAC address, and who basically made the request and everything. So basically at this MAC address here, and basically the IP address of the client that made the request. So I mean, so for the most part, pretty simple, not that much to really kind of to look at and everything, not that exciting of a protocol. But even though it's not that exciting of a protocol, it's a very dangerous protocol in the sense that it leaves you open for an attack, and mainly because of the fact, which is just like some of the other protocols too, the fact that they basically broadcast. So before we go into the lab, I'm gonna go ahead and knock out NDP. NDP basically is more or less for version 6 and everything. Basically does the same thing as far as trying to map out your network and everything, but it goes a little bit further in the sense as far as router advertisements and stuff like that. So it goes a little bit deeper. We won't look that deep into it as far as our lab and everything is concerned. We more or less just want to keep the correlation between what we have with ARP and what we have with NDP. But for the most part, you just want to take what gets the concept you want to take from dealing with NDP and dealing with ARP. NDP is basically IPv6 version of ARP, as far as basically mapping out, or in this case, you see the last bullet, trying to discover or figure out your network. So what your network paths and stuff are, which ARP don't necessarily concern itself with network paths, but it does try to figure out what other computers are on the network, who are my neighbors, who are the people that I can basically talk to. And if you look at IPv6 or the NDP, you see that it's a much simpler header. As you'll see with IPv6 and IPv4, there are 3 protocols. V6 have a smaller, well, it has less fields. I won't say that it's smaller, but it has less fields than its IPv4 cousin and everything. But it's still a bigger header in the sense as far as how many bits that it basically covered, because remember, IPv6 has 120, it's 128 bits, as opposed to V4 is 32 bits. So for the most part, you can see that IPv6 is the inner workings of that particular protocol. Looks a little it looks simpler as far as basically being able to read it and see what's going on with it and everything, but it is definitely still a bigger header. All right, so that's enough of me talking. So what we're going to do is, and like I said, try to get through these. Going to be a little quick as far as today is concerned, so we can make sure we get through these labs. So what I want you to do is, and let me close this. And I'm just going to drop this into, if you're not already there, drop this into the chat. All right. Now, what you're going to do with lab 5, so I want you to do lab 5 and lab 6. They should be pretty quick labs. So do lab 5 and 6. Before 6, what you're going to need to do is that share that we had yesterday. I'm just going to go back here and show you. That share we had yesterday, like I said, I didn't create no new folder or whatever, so you can still use the same folder. Go back to Maxmind databases, and you want to download this PCAP right here. So just download that. It shouldn't take that long. As you can see, it's only 19 kilobits. So just download that to your computer and everything, and then basically when you're ready to do lab 6, just open, well, it's going to tell you to open up this particular file. So you open up this file and then just follow the directions um, for lab 6. So right now it is 9:20. Like I said, those should be pretty quick labs to do. So around about 9:45, we're gonna basically see open up if you got any questions, and then we're gonna go ahead and move on to the next group of protocols. So go ahead and do that. I will mute my mic, but of course you'll still see me present if you have any questions or anything like that. So go to Moodle, do lab 5 and lab 6. All right, we may picking back up in about 2 minutes. All right. How many people still working, or need a few more minutes before we start on the next one? Or okay. So I don't know what happened with David. We'll wait for him a few more minutes. David, you still on, or just cut your camera off?
David, you okay?
May have gone for a restroom break.
Yeah.
No, I'm multitasking. I'm doing work orders.
Okay. Okay. We just want to make sure you're still
Yeah, I just-
engaged.
Okay, so make sure it's there.
Oh, yeah.
Okay. All right. So since you're there, so we'll go ahead and we'll bring back up my screen. So we're going to look at IPv. Well, just look at IP. Of course, dealing with you got 4 and 5. Not 4 and 5. My bad. 4 and 6. As far as IPv6 is concerned, think about something else. All right. So let's bring up my share. All right. So everybody should see me now. All right. So basically, just one thing too, I did add just before we move off from art, I did add um, a picture inside of it just so you can see the difference and the comparison between art and NDP, and basically the matchup. We more or less, as far as your labs was concerned, we looked at these two things here, the two top ones. But I mean, like I said, depending on I guess you could say how much traffic you basically gathering and everything, especially with IPv6. If you have IPv6 going in your network and everything, you'll see traffic or packets for basically both of these. But this particular table is more or less for you to kind of do the comparison. Of course, request, reply, you get solicitation on IPv6, advertisement for V6 instead of reply um, for solicitation, advertisement the same for router. Redirect is basically the same. As far as detection, as for V6, we just call that the gratuitous art. Basically, for the most part, like I said before, just making sure this is just something to help another computer from getting the same IP address that you have. And then, of course, as far as the table, IPv4 for ARP is called ARP cache, and then it's neighbor cache for V6. Everything. So I did drop this into Moodle. and everything. You should be able to download it, but if you can't, just let me know. I'll make sure you're able to download it for your own future reference. So of course, dealing with IP, just like we dealt with as far as um, network discovery. That's what I basically will call both of those protocols, as far as basically finding out what's on your network and everything. You have two versions with IPs. You got V4 and you got V6. V4, for the most part, I think as of 2015, we basically ran out of IPv4 public IP addresses. So for the most part, there's other than our private IP addressing that you have inside your network, there's really no more IP addresses to basically be divvied out. For the most part, there's a very slow molasses-like um, transition into IPv6. Most of the world basically has went to IPv6. I guess my own um, opinion or whatever I feel is that for the most part, because the United States pretty much invented, I could just say, internet or the networking and everything, we pretty much have all the IPv4 or almost the IPv4 addresses. So for us, it's not much of a it's not as much of a need or necessity for us to move to IPv6. Most of the world, pretty much more, in other countries, are more or less have bigger V6 networks than we do. And then when you throw in the classless networking with our subnetting and stuff like that, I mean, like I said, just the necessity for us to really move to V6 is not as prevalent in the United States as it is around the rest of the world and everything. But for the most part, both protocols basically does the same thing as far as transmit. Their purpose is to transmit and deliver data between different networks. Of course, you know what you're dealing with your routers. Routers is basically on layer 3. So you normally using your IP, your logical IP addressing to traverse between the networks. So there's really no true difference between, there's no difference between V6 and V4. One of the things that you do get with V6 that you are able to add more security and everything like that, because when V6 came out, or when they would start to design V6, our networks, it wasn't, or people started to see that we can't trust our networks as much as we thought we were going to be able to. So when V4 was created, I mean, it was a little more trusting, thinking along the lines of, hey, who would do the things that basically people are doing now. V6, for the most part, been able to implement IPsec, IP security, being able to better implement encryption and everything. So you get those features with V6 natively, whereas with V4, you have to use other um, techniques or whatever in order to basically be able to provide security for V4. And as you see, as far as the bullet is concerned, just basically been networked for decades, has a simpler header structure, as I mentioned earlier, which you're about to look at later. Um, but for the most part, perform the same function and everything. So they're not, even though they look different on the wire and everything, but they pretty much serve the same purpose. Primary tasks for them, just I mentioned earlier, of course, they deal with fragmentation, addressing, deal with routing. With WV4, as far as dealing with fragmentation, basically, fragmentation can happen at the sender and the router. Basically, um, when you basically fragment packets, anything like that, for instance, somebody send, say, a jumbo packet, or if you do a ping, and basically send something that's bigger than your MTU, basically, which is 1,500 bytes, basically that particular packet would have to be fragmented. Well, with IPv4, that could be done at the source and at the router. With IPv6, that's only done at the source. The router don't necessarily, if a version 6 doesn't necessarily deal with fragmentation, anything like that. Of course, addressing is, of course, is still the same. Same thing as dealing with routing. Only thing is that you're just dealing with a bigger with a bigger header, in a sense. Like I said before, IPv4, you're dealing with 32-bit. Before you're dealing with 32-bit, with IPv6, you're dealing with IPv4, you're dealing with 32-bit. IPv6, you're dealing with 128 bits. But other than that, not really of a true difference between them, other than I would say more or less size. And IPv6, like I said, does give you a little bit more, options as far as dealing with security. Basically, support security more natively than say IPv4 does. All right, so let's go into our header right here. And basically what I want you to see here, and I'm just gonna pull up Wireshark on my computer. I was just trying to have it look at it on the host computer for you guys, but I'm gonna go ahead and do it on, let's do it on my computer here. So we can just look at it. Should have enough here. And let's just do IP. See if I should have some IP traffic, hopefully. Not much. Okay, let's just do it ICMP. Do this real quick. Just create some IP traffic real quick. Just do ping. And I just do one. I'll do 168. 0. Well, that's not 0. And I say 1. All right, so that should give me some traffic there. Okay. Yeah. All right. And I'm gonna do ICMP. ICMP. All right, so that's good. Now stop this real quick. And okay, so there we go right there. Okay, so this give me some IP4 traffic right here. And basically what I want you to see here, and just pull up my slide again and move it just a little bit and make it a little bit bigger so you can see it. Oh, didn't do that. Okay. So I want you to just see here, just like we did with the ARP, you basically can see that these are the same. You got your header version, your header length, your DSF, your total length. And that's what my ESN basically just part of that particular field there. Your identification, flags, basically so on and so forth. So pretty much, like I say, as far as the diagram that you see here is basically the same here. So I'm gonna shrink this here so we can just kind of look at it here. So basically, of course, dealing with your header length, basically just telling you the length of the header basically altogether. Majority of the time, that's going to be 20 bytes. Not too often is really going to be more than it. That's pretty much going to be the default that you see there. As far as version, we know this is version 4 because, I mean, when you see it there. So as far as the version, so of course, with IPv6 is going to say 6. 4 is going to say 4. Like I said, the bytes length size normally going to be 20. Now, as far as dealing with DSF, this is basically normally when you're dealing with quality of service. So if you got any type of quality of service like voice over IP, stuff like that, or just really just thinking along the lines of any type of traffic that you're going to apply any type of QoS to, normally you're going to see that type of traffic, or you're going to see these fields or these values change based on that. Now, if you got regular traffic, basically, like as you see here by default, is going to be 0. Total length, basically, like I said, that will change and everything here and there, but for the most part, just giving you the total length of the header as a whole. Not the header as a whole, but information that you have as a whole. Now, identification, for the most part, basically is just going to be more of a 16-bit value that's going to basically just identify the information that you have going across basically the wire, what's basically in your data stream. Now, your main important part is here, basically with your flags. Normally, this right here is going to be dealing with your fragmentation and stuff like that. So basically, as you see here, this right here is pretty much as you see your reserve bit. And this right here is basically if you don't want it to do any fragmentation. So basically 0, I can um do fragmentation. And then here, basically, I got more fragments coming. So if it's 0, basically, you see a packet come in, say if it's in a list of fragments. So you'll see multiple packets, and each one of those packets will have the same ID number to on it. So basically, you say, for instance, here, you have the same ID, but you'll see um, this particular flag for each one of those packets will be 1, 1, 1, 1, and then the last one will be 0. So that basically just saying no more. Well, I got it backwards. Yeah, no more to come. One basically means I got another one coming. Well, then so each one from say just say right here I have a um, fragment here. Say all these are basically fragments. So basically this one here will be set to 1. More fragments set to 1, 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 and then this one right here, more fragments will be set to 0, meaning that basically no more. This is basically the last fragment. Nothing else will basically come through. And the reason why I wanted to highlight that this particular header or this particular field here is mainly because of the fact that as an obfuscation technique that attackers will basically use if they're trying to send any type of malicious code or anything like that, they will just fragment or they'll send a packet that's basically bigger than what you can actually handle, which by default is really 1,500 bytes. So they send a packet that's basically, or they send their packets in a way whereas it's going to be more than 1,500 bytes. Your network or well, I'll just say your network. Basically, that packet would have to be fragmented. And the problem with that is that when you send a fragmented packet, all your networking equipment by default does is just sends it. It don't check it out. It don't expect it or anything like that because I mean, if your routers and everything had to basically take a packet, reassemble it, see whether or not it's got bad code in it or not, or bad traffic in it or not, and then disassemble it again and then send it out. I mean, that's just going to take forever in a day. So normally reassembly normally doesn't happen until it gets to its destination. And that's when the reassembly basically comes back into play. The problem with that is, especially into today, is a lot of companies, a lot of people, and it's just not companies, but even at home, don't have any host-based or endpoint-based type of protection. Or if they do, they don't keep it up to date, so on and so forth. And the thing is that once that packet comes to wherever it's going and it gets reassembled, anything that's going on that's basically that particular packet is made for is going to run on that computer or that device or whatever basically that packet is destined to. And seeing what your host base base equipment or technologies do for you is that it'll reassemble that particular packet or data, and we're running in basically we'll say a sandbox and everything to see how it basically will behave, what it's going to basically do, and then depending on the protection that you have, it'll either drop it, not let it run, put it in quarantine, so on and so forth, and everything. So in a sense, you kind of, for the most part, was thinking along the lines of security. Your networking devices, unless they was designed to do something else or whatever, normally don't check for fragmentation. It just basically allow it to go through, and that's not irregular traffic. That's nothing that basically you will get um, um, alerted to unless, like I said, you have another device or you have some other protection in place that will warn you or alert you that that's basically happening. But just for the most part, by default, as far as where your networking equipment work, um, as me as an attacker, if I want to obfuscate your router, well, even if your router as far as ACLs are concerned, but your firewall, anything like that, I can send a fragmented packet towards your way, and then basically once it get to to the destination, that particular attack will run at that particular moment. Now, as far as Wireshark and as far as analysis, anything like that, um, I would say if you're trying to inspect a packet, whatever, you pretty much kind of want to see whether or not a packet is part of a fragment or not. So basically, if you see where packets that came before it, and I'll say in a line, for instance, here in the line of a conversation, you can basically, you have to get that whole line of communication, basically have it reassembled to see the full um, purpose or the intent of that particular packet. Because if you just get part of it, then you're only getting part of it. If you're getting one that's basically has a fragment, or this is basically set to one, then you don't have the whole thing. You got a piece of the puzzle. So definitely you want to look at that as far as dealing with when you're doing your analysis and making sure you don't have any fragments or whatever that's going on with your particular package. Now, as far as fragment offset, basically that's just help you indicate where a fragment basically belong within a sequence. Time to live, I think that's pretty self-explanatory. But for the most part, how many normally hops that they basically take before the packet would just basically be dropped. So after 128, that's basically it. If I take 128 hops, say what you can say routers or whatever you want to basically call it. And normally it is routers, but in this particular case, you see my time to live. I'm not going through a router to um, get my. I'm not going through a router to get a reply to my request. So when you're dealing with the internet, this normally basically you're dealing with hops, and normally, like I said, from one hop to the next, that's normally a router. But for the most part, this is how many times the packet will basically go out, or how many tries it will basically, how many tries it will basically take before it just be like, I'm just going to drop the packet, not unnecessarily worry about it. Header checksum. For the most part, that right there is just going to really just give you calculated for the accuracy of the hop. For every hop, it ensures accuracy. So basically, when it goes, basically drops. So you say it starts at 128. Next time, basically, it'd be 127, 126, so on and so forth. All right, and then of course you got here as far as your source IP address, destination IP address. Pretty can kind of tell what that's basically is. So depending on the packet that you chose, of course that'll be the source for this particular packet, but just understand that that could change from packet to packet. All right, so let's go to IPv6 header. I'm gonna open up that because I should have it before. So I'm gonna open up that PCAP that you guys are gonna be using. So let me go to open traffic, continue it out. And let's take this out here. See what we got. All right, so dealing with IPv6, I can still choose a IPv. So dealing with IPv6 right here. So go back. So as you see here, as far as dealing with IPv6, the header course has less fields than what you have with IPv4. So as you see, IPv4 has way more fields than IPv6 has. But the main thing that you want to look at is, and that shouldn't be 32, that's a typo here. Basically, going across, basically, it should be 128. So you got 128 here, 120, of course, for dealing with your IP address. So basically, as far as your um, address and everything is concerned, basically, it's going to be a little bit bigger. Well, I won't say a little bit bigger. It's actually way bigger, about 4 times bigger than, say, IPv4 header. But for the most part, you're still dealing with the same type of information. As far as version is concerned, and I just want to pull this down a little bit so you can see it on both ways. All right, so you can see same thing like I said before, version. You're dealing with IPv6. You can see the bit version of as far as dealing with IPv6. Then the class. Now this is the same as your quality of service. This deal with quality of service just like you did in your IPv4s when you're dealing with your DF, not DF, but your DSL or your DS C code and everything as far as dealing with IPv4. So basically, your traffic class is more or less going to be dealing with, and it's kind of showing you right here to your DSCP protocol point. So your differentiated service code point right here. So basically, they are the same thing as far as dealing with IPv6 going to IPv4. And then dealing with your flow label, the main point as far as that is basically you don't ever see in that too often or any let me see right here. So as you see here is basically nothing there. You ain't gonna see anything there too often. That's more or less more of an experimental type of feel. So normally when you're looking at IPv6, you're not gonna necessarily see any values as far as that is concerned. Payload length, basically just telling you how big the payload is going to be. In our particular example here, you see that that's 40, but basically it would change based on the length or basically how big the actual payload needs to be. Next header, that's more or less pretty much will kind of tell you what's in this sense, what's the next protocol. If we look right here, that is the equivalent of right here. So you see we got your protocol here. A lot of times you'll hear that called the upper layer protocol. That's basically the same thing when you're dealing with V6. That's what the next header is. So that's just telling you what protocol I'm going to basically be using next, or what's the next header. So in this case here, our upper layer level protocol, or the next header or the next protocol header that I'm going to basically be dealing with is going to be ICMP, which of course you see here. And the reason I'm kind of, I guess, going through it like this because of the fact a lot of things that you see in one header, just looking at Wireshark, you could pretty much see the clue for it in basically in your details page. So as you see here, you can already see the ICMP is the next header because of course, like we were saying before, layer 1, 2, 3, and then of course ICMP still works in the I guess you can say the layer 3 RAM and everything, but it's still the next protocol that's as far as going up, this next upper layer or the next protocol up from IPv6 or IPv4. So in here it's just telling you as far as the next header, not IPv, but ICMP is my next protocol. And then hop limit is the same we did with TTL. Of course, as you see here, still 128. And then of course you got your 128-bit source IP address, 128-bit destination IP address. So for the most part, pretty similar and everything as far as their of course their purpose and everything, even though IPv6 changed as far as this header is concerned, but a lot of the information that you'll look for in IPv4, you can find the same information in IPv6. Now some stuff of course was taken away, as you can see here. You don't necessarily see anything as far as fragmentation or anything like that, because like I said, once this packet really, you're not going to do too much fragmentation as far as dealing with IPv6 anyway, but when it gets to the router itself doesn't necessarily deal with fragmentation. You would do that at the source. And I didn't put it in our slides before I let you go, but I did put another, go back here, as far as IPv4 comparison. So you can kind of see the difference between the two. So as far as IPv4, has a checksum, C6 does not. The main thing I wanted you to see as far as it was concerned about the fragmentation. Okay, here must support to give you the packet size that it has to support, can be fragmented. As you see here, it's not fragmented. Now, like I said, that's why you don't see that in the IPv6 as far as fragmentation, because it does not handle or deal with fragmentation. But you can have fragmentation say in your trace for on the IPv6 network, but you won't see it as far as dealing with the protocol itself. And then of course, as far as we saw this from ARP protocol, as far as dealing with discovery, as far as how it basically does its discovery. And of course, as far as V6, dealing with ICMP, you go on solicitation, route advertisement, and then basically just going through as far as how it deals with its options field. IPv4 doesn't have packet flows for their QoS. IPv6 does, but like I said earlier, that particular field is normally not set. No values applied to it and everything. And then basically, as far as including the checksum, IPv6 does not. IPv4 does. All right, so well, we can stay here. So for your labs, we've got one lab for your IPv for IP, which is basically just going to be IPv4. You're going to create your own traffic. Like I said, when you go through the lab, it's going to walk you through step by step. So you're going to create your own traffic for that particular lab there. It is 10:14. I know our break is at 10:20. So I said about 15 minutes plus, so we'll say around about 10:40. We'll get back started. That's with including your break. So basically take about 15-20 minutes on the lab, and then of course 15-20 minutes on the lab, and then take about 10 minutes for your break. So we're looking at about 10:35. So 10:35, we'll basically come back, get started and everything. So I'm just trying to make sure we got the time and stuff right. So it's 10:14, 10 minutes. That'll put us at, that'll put us at 10:25, about 15 minutes. So yeah, about so like I said, about 10:40. About 10:40, we will start back. I will let everybody know, and then we'll pick up on our next protocol. All right, so I'm gonna mute my mic and unshare.
Are we taking a break now?
You could take it now. Yeah, you could take the break now and then start on the lab, or you could start on the lab and then take the break. Doesn't really matter. But basically, our time is basically including the time for the lab and the break.
And come back at 10:40.
Yeah, come back at 10:40.
Gotcha.
Yeah. With the lab completed.
Yeah, with the lab completed. Yeah.
Yeah. Okay, Deej, I'm gonna mute during the break.
Okay.
All right.
All right.
Annalise, I think we're good. We're breaking right now, but I think we're good.
Okay, sounds
Yeah,
good.
thank you for checking in.
Of course.